Hello, Doctor. My name is Bugasha Muhammad Abdurrahman, and I am the leader of this group. Today, along with my teammates Ayub Sharfawi and Yusuf Shalafi, we will presenting our project titled Applications of Any Values and Any Vectors in Science and Engineering. We will explore in our presentation how these concepts are applied across several fields, including civil and mechanical engineering, electrical and control systems, as well as physics and data science. To begin, Yusuf will explain how any values and any vectors are applied in civil and mechanical engineering.
Okay, thank you, Muhammad. Hello there, my name is Yusuf Ashalafi. Today I'm going to explain about the applications of eigenvalues and eigenvectors in civil and mechanical engineering. So first of all, we are going to explain what is what is the applications about eigenvalues and eigenvectors in civil and mechanical engineering. So if we speak about civil engineering, so eigenvalues helps or help to analyze how buildings and bridges respond to vibrations like wind or earthquake. So they are used to find the nature of frequencies and avoiding resonance. In mechanical engineering, they are used in car suspension systems to check if the system is stable, overdamped, or underdamped. So first, we are going to explain the main idea of what are the eigenvalues and eigenvectors itself. So in linear algebra, eigenvalues and eigenvectors are used to understand how matrix transforms a vector. So if vector only changes in size but not in direction, then it is called an eigenvector. And the amount it gets stretched and shrunk is called the eigenvalues. So this idea is useful in engineering, especially when we study vibrations. So now we are coming to uses in civil engineering. So in civil engineering, eigenvalues help engineers analyze how buildings and bridges respond to vibrations from earthquakes, wind, and traffic. So how this is happen actually? These vibrations are first modeled using differential earthquakes. Then these equations are turned into matrices. So when we calculate the eigenvalues of these matrices, we find the natural frequencies of the structure. That means we know at what frequency the building or bridge will vibrate naturally. But what is the danger actually? Actually, we are going to explain the danger of this. So if an external force like wind or an earthquake, for example, has the same frequency as the natural frequency of the structure of this bridge, so this causes resonance. But the danger when this resonance can make the vibrations stronger and stronger until the structure cannot stay and it's gonna be collapses. So this is why eigenvalues analysis critical in the design phase. It helps engineers change the design to avoid dangers of these vibrations. So when we come to mechanical uses of these, we can say that in mechanical engineering, eigenvalues are also used to design car suspension systems. These systems help the car absorb shocks and stay stable on the road. So how is this actually happening? Engineers use matrices to model the suspensions system and calculate its eigenvalues. So the eigenvalues tell us if the system is stable, so it's not moving that much, it's not extra motion, and also tell us if it's overdamped, so it's very response to anything coming from outside, and also tell us that it is underdamped, so it's not that much bouncing. So now Muhammad is going to continue explaining about the applications in electrical engineering and control systems.
Hello again, I am Mohammed Abdurrahman Bugasha, and I will be talking about the role of any values and any vectors in electrical engineering and control systems. In electrical power systems, any values are used to check whether the system is stable or not. We model the system using matrices in what is called state space form by calculating the any values of that matrix. We can tell if voltage and currents will return to normal after a disturbance. If uh, if all the any values have negative real parts, it means the system is stable and behaves safely. For example, in power grid, engineers use any values to ensure that voltage levels return to normal after a sudden change in load. RLC circuits can be modeled using matrices that come from Kirchhoff's laws. By finding the any values of these matrices, we can understand how the circuits behaves over time, whether the current will oscillate, slowly decay, or become unstable. This kind of analysis helps engineers design circuits that are reliable and perform as expected. For example, in radio tuning circuits, any values help determine how quickly the signal settles to the desired frequency. And now in control systems, uh, in robotics and automation, control systems rely heavily on any values to ensure that response are both fast and stable. The position of the any values tells us how the system will behave, whether it reacts smoothly, overshoots, or became unstable. Engineers use a method called any value placement to adjust these values and design systems that respond quickly and accurately. For example, in robotic arms, any engineers place any values to ensure smooth and precise movement without vibration. Now, let's move on to our final speaker, Ayub Sharfewi, who will explain how any values are applied in data science, image processing, and physics.
To my friend Mohammed and Yusuf, and our third slide is about the application of eigenvectors and eigenvalues in data science, image processing, and physics. Firstly, we will start by the application of it in the data science. Firstly, it helps to reduce data set dimension while preserving key information. The PCA, or principal component analysis, reduces high-dimensional data like images with more than 1,000 features into a smaller set of principal components between 10, 20 or less or more that retain most of the important information. This simplifies the data, avoids the curse of dimensionality, and improves algorithm performance, which means that the eigenvectors and eigenvalues help the PCA to to make the data smaller but keep the main information. Secondly, the role of eigenvectors and eigenvalues. In PCA, eigenvectors represent the main direction of variance in the data that exists along which the data spread the most. Eigenvalues indicate the importance of each direction by measuring how much variance information lies along each eigenvector, and we can see it in this graph of principal component analysis, the PCA, how the eigenvectors is used, and it helps to the eigenvectors and the eigenvalues is used and help to identify the set or the direction. Thirdly, the covariance matrix. The PCA starts by computing the covariance matrix, which shows how features vary together. This reveals patterns in the data and helps determine the direction of maximum variance, which is quite related to the second one and direction, and we can see it in this graph. Secondly, the image processing. Firstly, we will start by facial recognition with eigenfaces. Eigenfaces is a facial recognition technique that uses PCA to analyze a set of face images and extract key features. Each face is represented as a combination of eigenvectors called eigenfaces that capture the most important facial patterns. This allows the system to recognize new faces by comparing them to known patterns. Secondly, we will discover more and more how it works. The system first applies PCA to a dataset of face images to find their principal components. These are the eigenfaces. Each face is then projected onto this reduced space, turning it into a set of ways to recognize a new face. The system compares its ways to those of known faces and finds the closest match. Thirdly, we'll know why it works. Eigenfaces work because they capture the most important variations across many faces, like the general shape of eyes, nose, or mouth. By focusing only on this key feature and ignoring minor details, the system can efficiently recognize faces while reducing noise and complexity. Which, like the sum of this slide, is that we use the eigenvectors to transform it into eigenfaces, and then we can recognize each face by focusing on like the main components of the face, like mouth, nose, and eyes, and ignore the small details. Thirdly, the application of eigenvectors and eigenvalues in physics, which is one of the most related fields into linear algebra. Firstly, we will start by eigenvalues in quantum mechanics. In quantum mechanics, many problems involve solving the Schrödinger equation, which is one of the most known equations in physics and quantum mechanics, and as we can see it here in the picture, which becomes an eigenvalue problem, which is the equation goes from a quantum mechanics problem or physics problems into just an eigenvalue problem. The system's behavior, such as the allowed energy levels of an electron is determined by the eigenvalues of a special matrix called the Hamiltonian. Secondly, the role of the Hamiltonian matrix. The Hamiltonian matrix represents the total energy of quantum system, including kinetic and potential energy. Solving for its eigenvalues give the system's possible energy level, while the corresponding eigenvectors describe the quantum states or wave functions, which we can know the Hamiltonian matrix helps too much in determining the levels of energy, which is one of the most important problems in the quantum mechanics and physics. And thirdly, the real-world significance. These eigenvalues explain why atoms emit or absorb specific wavelength of light. Each jump between energy levels corresponds to a quantum of energy. This concept is key to technologies like lasers, quantum computing, and MRI machines. And in this one, we can see the relation between the eigenvalues and the light and the energy in physics. In the conclusion of our presentation, we can know the importance of eigenvalues and eigenvectors and its application in science and engineering. And thank you for watching our presentation.